Okay, so let's get going. So what I want to talk about today is the idea of recursive types, which are going to connect up to the previous lecture that Bob just gave on recursive programs. And what we're going to see by the end of the day is how recursive programs actually fall out of having recursive types. But before we can build up to that, I want to start with a few more basic things that we haven't really had a chance to get on the board during the course of the summer school this year, which is product types and sum types. So we'll need these as a tool for what we're going to do today. So let me just quickly talk about what's going on here. So maybe you've looked at some of the hands-on problems about this. Maybe you've seen this before. But the idea is that a product type, which we'll write as tau1 cross tau2, of course, represents pairs of a value of tau1 and a value of tau2. And so if you would like to make such a thing, then you can pair together an E1 and an E2 to get a tau1 cross tau2, where E1 has tau1 and E2 has tau2. And then if you'd like to use such a thing, then there's two ways to do it. If E has type tau1 cross tau2, then I'll write it as FST for first projection of E has type tau1, and if E has type tau1 cross tau2, then I'll write SND for second projection has type tau2. Okay, so I know many of you have seen this before, but I also know that many of you haven't, and so I just want to fix the notation there. So the idea is to make an element of a pair type, you give two things. To use an element of a pair type, one way to do it is to say that, well, if I have something that will reduce to a pair, then I can take its first projection, I can take its second projection. And then the dynamics says that, well, the key instruction steps are that the first projection of the pair E1, E2 steps to E1, and the second projection of the pair E1, E2 picks out E2, and we'll have rules like the first projection of E will step to the first projection of E prime if E steps to E prime, so that we can look for a pair in the argument to take the first projection of. Okay, suppose we want our pairs to be eager, or suppose we want them to be lazy. What do we do with these dynamic rules? So if we want lazy, let's say, what do I change about what's on the board? We're good, right? So if you want your pairs to be lazy, then the only thing I need to say is that the pair E1, E2 is a value regardless of whether E1 and E2 are values, right? So like in the previous lecture, Bob was talking about whether natural numbers are eager or lazy. What that means is successor of blah a value, or is successor of blah a value only when blah is a value? Okay? So if we want lazy, then we do that. If we want eager, then what do we have to do? So we change this to be a pair of values is a value. And then we would want to put that up here too. So these bracketed ones are there for eager and not there for lazy. And similarly over there. And then, of course, we have the same step rule there for second. What else do we need to say?
We need to step the first part of the pair.
E1, E2 steps to E1 prime E2 if E1 steps to E1 prime, if E1, E2 steps to E1, E2 prime if E1 is a value and E2 steps to E2 prime. Okay, so these kinds of things are there if it's eager and not there if it's lazy. That is, if you want something eager, then you'd better have rules that say, well, when you see some brackets, evaluate the inside. Otherwise, if it's lazy, you would just say it's a value like that. Okay? Where would you notice if you forgot those rules? What theorem would fail? Yes, type safety, but in particular, which part of it? Progress, right? So if progress says if E is well typed, then either E is a value or there exists an E prime with E stepping to E prime. So suppose you had something like that and you intended, well, suppose you had something like, to be concrete, 1 plus 2, comma, whatever, and you intended the language to be eager, but you forgot the rule that says step the inside of a pair, then this is not a value if you have these premises on the value rule, but it also doesn't take a step if you forgot that rule. Okay, so that's a little bit on pairs and eager and lazy interpretations. Let's do sums, just so we have them on the table. So we're going to have a type tau1 plus tau2. The constructors will be in left has type tau1 plus tau2 if E has tau1, that if, let's call that E1, if E2 has tau2, then the right injection of E2 has type tau1 plus tau2. Okay. For pairs, what we said was the value consists of two things. Therefore, there's two things to take out, first and second. For sums, we say the values consist not of a pair of two things, but of a choice between two things. So how do we undo that in the elimination form? If we know that a value of this type is either of this form or of this form, that's what motivates having a case analysis principle where in left of x1 goes to something, or in right of x2 goes to something, as our elimination rule. Okay? So the elimination rule for sums is a case because for sums there are two ways to make a value. Therefore, we need to check which one of those was used when we take it apart. Okay, so suppose E has type tau1 plus tau2 to have a case. Well, in one branch we got a tau1, and in the other branch we got a tau2. And if no matter whether we got a tau1 or we got a tau2, we can create something, then overall we can create something. Okay? So that's the idea with the case. And then the operational steps are, of course, if I'm case analyzing in left of some E1, and my branches say in left of X goes to E1, or in right of Y goes to E2, then where do we proceed to there? Oh, okay, that was bad. Call that E. Then we'll get E for X in E1. If, on the other hand, you have case in right of same thing goes to E2, then the case selects, or E for Y in E2, the in right branch. If we wanted to make our sums lazy, then what's a value? in left of E is a value separately, in right of E is a value. If we wanted to make them eager, then when is this a value? Only if E is a value. And it's the same kind of deal up there, right? So if we want to make it eager, then we need to step the inside of it in left. Otherwise, progress would fail. If we wanted to make it lazy, then we don't need to step the inside. In any case, we need to step the principal argument to the case, right? There's a search rule there that says case E steps to case E prime if E steps to E prime, because we need to look for a value to step on here. Okay? Do we ever run the branches of the case? Are there step rules for the branches? No, that would be weird, right? Like we tend not to run open code. You don't run the branches of a case until you actually get to the selecting the one that you're going to run. Okay, so good on products and sums? Because we're going to need them, yeah.
That should be x1 and x2 in this bracket.
Yes, thank you. Other typos? Yeah, so there's lots of rules I didn't write here. Yeah. I was just kind of hand waving at it. Okay.
The rules on the left,
Yeah.
if you have gamma entails E1 to the type T1,
Yeah.
that proves it's not rule.
Yeah.
How are we getting the tau to?
Yeah. So if you look at the hands-on problem on this from day one, formally the in left is annotated with both tau1 and tau2. Or maybe you might annotate it with just tau2, though that's pretty confusing to read. The idea being that if you want to set up your type checker so that every term synthesizes a unique type, then you would need some information here in order to know what the other side of the sum is. On the other hand, there are other ways to set up type checkers so that instead of always synthesizing a type, you do what's called bidirectional type checking and push types in from the outside sometimes. If you're doing that kind of thing, or if you're doing Hindley-Milner type of inference, then maybe you could forget about that annotation. So if you look at PFPL, there's a lot of places where in the formal syntax there's some annotations, which we leave off in actually writing it when we can kind of, as a person, figure it out. Okay, good? Okay, so now that we have products and sums on the board, what I want to do next is to talk about how certain inductive, co-inductive, recursive types arise from products and sums. Keep that up there. Okay. So, what are the natural numbers? So let's just, for now, suppose that everything is call by value / eager. So we do the eager thing that we just talked about for products and sums, and we evaluate the arguments to functions before we step into the body of a function. We can characterize the natural numbers as an equation, which I'll write like that, which stands for a type isomorphism between two types. On the one side, we have the natural numbers. Oh, and actually, the other one is not a type that I wrote on the board, so I should write it. There's a type called unit. There's a value like that. Okay? So unit, remember, products were types where you have a pair of two things and two projections. The zero-ary case of that is a type where you have a constructor that has nothing inside of it and no projections. Okay? So this is the type with exactly one value. So what can we say about the natural numbers? We can say that it satisfies the following equation. N is, in a sense, the same as unit plus n. Okay. So this notion of type isomorphism will be exactly the notion of isomorphism that Ed was talking about in his lecture yesterday, which means to give a type isomorphism means to write functions back and forth that compose to the identity. Okay? So let's explain why nat is isomorphic to unit plus nat by witnessing that with some functions. Okay? Which direction do you want to do first? I have a vote for that way. Okay. So what does this mean? It means we need to write a function that takes a number and returns that stuff. So it can start off lambda x colon n dot something. What can we do with a natural number? Well, we can do a rec, in which case we have to send 0 to something, and we have to send successor of y to something else, maybe with the recursive call, and then we would apply that rec to x. If I want a value of type unit plus something, then what I'm going to do in each case is to do an in-left or an in-right, because those are the constructors for plus. So which one do you want for 0? What do you want for successor? Okay. Inside of a natural number, what you'll find is either no more information if it's 0, or another natural number if it's successor. Okay? What about coming back the other way? Lambda, I don't know what to call it, z unit plus n. What do we do with a sum? We case analyze it. Case z of, if it's in left of I don't care, then we'll do something. And if it's in right of, let's call it y, then we'll do something. What syntax did I use up there? The hooks. Okay. So where should we send in left of whatever? 0. Where should we send in right of y? Okay. Why do these two constitute an isomorphism? That is, why do the maps back and forth compose to the identity? Well, suppose we start with 0. That gets sent to in left of the empty tuple, which gets sent to 0. Good. Suppose we start with a successor. That gets sent to in right. In right gets sent to a successor of the same thing. So we're back to where we started. Suppose we start with in left. That gets sent to 0. 0 gets sent to in left of the empty tuple. So in left of anything gets sent to in left of the empty tuple. Why is that getting back to where we started? Yeah, right. So one of the things that a good equational theory would let you prove about unit is that anything is observationally equal to the empty tuple at unit. Right, in particular, at the type unit. Why is that true? Well, for all no observations that you can ever make about the empty tuple, those behave the same. Right? If you can't do anything with a type, then observational equivalence should equate everything. Okay. Good on n being that thing, or at least good on n having that property. Suppose we have a fixed type tau. What equation does lists of tau satisfy? Yeah. So like, if we were to say it out loud, any list is either the empty list or it's a cons with a tau and another list. How do we write that as a type equation? Good. Okay. What are the functions? Well, suppose I have a list if it's empty, I'll give back in left of the empty tuple. If it's x cons x's, then I'll give back in right of the pair of x and x's. And you can imagine what the converse one in the other direction is doing, since it's just shuffling around constructors like that. Okay? So what we've got is this idea that types can be characterized, or at least certain inductive types like nat, are solutions to equations of the form t is equal to something of t up to isomorphism. Okay? Nat solves the equation if we were to write that out as a type t, a thing with a type t free, it would be t dot 1 plus t. List of tau solves t dot, oh, sorry, I'm slipping up here. So in more mathematical notation, people will often write unit as 1 and void as 0. But when we're talking about natural numbers, it's confusing to use that for both the types and the numbers, so I'll try to avoid it. List solve t dot unit plus tau cross t. Okay? So the idea is that n is a solution to, n is isomorphic to 1 plus n, unit plus n. We can write out the template of that equation as a type with a free type variable. We can write out the template of this equation as a type with a free type variable. And note that n and list are solutions to those equations. Okay, now the thing I keep stumbling over, because I haven't said it yet, is the idea of, given an equation like this, how many solutions does it have? That is, does it make sense to say n is the solution to that equation? Or might there be many types that have that property that they solve that equation? Any ideas? So in a total setting, we can talk about inductive versus co-inductive types, which are respectively the least and greatest solutions to equations like this. Okay? So if we want the natural numbers, what we want is the smallest or most restrictive type that solves this equation. What does that mean? To solve this equation means that it has the function we wrote coming from this, right? Like we wrote the function in this way. What did the function that we wrote in this way, it's gone now, but, well, we've got, no, we don't have it. What did the function that we wrote in that way do? It selected 0 and successor, right? The function from unit plus n to n picks out 0 and successor. Okay? So having a function there tells you that you have 0 and successor. and saying that we want the smallest type, or the least fixed point, or the least solution, is saying that we have the smallest type closed under 0 and successor, which is exactly the natural numbers, right? It's giving us this idea that every natural number is either 0 or successor of 0 or successor of 0, and so on and so on and so on. Yeah?
How do we know that we want the smallest or least solution? Or do we always want the least solution?
Well, so what I'm trying to argue is intuitively is that the natural numbers have the property that they are the least solution.
Well, yes. But
Okay.
then we could also have a greatest solution to the,
Yeah.
to the equation?
Yeah.
Right.
Yeah. So what happens if we think about the greatest solution to this equation? So I'm going to write it in a slightly different notation, which will suggest what it is. Okay. So if we think about the greatest solution, then what we're saying is intuitively, it's the biggest thing that's closed under 0 and successor. Okay? Think back to the hands-on session when Bob went over operations being closed under, sets being closed under operations. We're saying it's the biggest thing closed under it. In particular, the biggest thing that's closed under that includes successor of successor of successor of successor of successor of forever. Okay? So the co-inductive or greatest fixed point, greatest solution to this equation will include an infinite natural number, which is sort of the lazy chain of as many successors as you want, and other infinite natural numbers. So we'll call, So we'll call it n infinity or n omega because it includes n in infinity. Okay? Similarly, if you play the same trick with lists, then the least fixed point or inductive interpretation of lists is lists, that is finite lists, that is everything's built from nil and cons. The greatest fixed point, or the co-inductive interpretation of lists, is what? Streams that may be finite, right? So it's maybe a finite list, or it's maybe an infinite stream. Okay? So there's this idea that depending on how you solve the equation, least or greatest, you'll get different types. Okay. So I won't go through the rules for inductive and co-inductive types. You can see the chapter in PFPL for that, because I want to move on to talking about this kind of idea in a non-total setting where things get to be a little more interesting. Okay, so the key idea we had now was that, yeah? Oh, yeah.
So when you say the greatest solution,
Yeah.
it sounds to me like we want to pack as many elements as we can into that set, like the set or the type of natural numbers.
Yeah.
Is that,
It's like the greatest thing consistent with the fact that it's closed under those rules. Right?
okay, so for like, so what we can do is we can add omega
Mhm.
to the natural number,
Yeah.
essentially, and the mapping just takes omega to inject right and omega like this. Okay. But why can't we just add more omega?
Well,
Arbitrarily big numbers. Because that sounds like it would produce a greater set, and you could just map them.
yeah.
So in what sense is this great?
It's greatest in the sense of, like, I didn't have time to go through like the universal properties that explain what it means, but basically, like, you can set up kind of category theoretic universal properties and then say that, yeah. So like, I think I'll have to like beg off on that one just because it would take too long to answer. But we can go over it after or during the hands-on session. So like thinking of it as sets is just an intuition. Really, I'm talking about sort of inductive and co-inductive types. But to a first approximation, that gives you some intuition, hopefully. Yeah. Yeah. I mean, yeah. Anyway, like later. Okay, so good. Where are we? All right, so what we're going to do is to introduce a new way of making types, which is called recursive types. And the idea is that what we're adding to our language with recursive types is essentially a postulate that equations of this form have solutions. Okay? So you want to think of the type, which I'll write as rec t dot tau, which will be a type in delta when, assuming that t is a type, tau is a type. Okay, so just like this equation, n is unit plus n, we sort of wrote out the schema as a type with a type variable. The new type constructor will take a type with a type variable. And the idea is you want to think of this as the or a solution to t is isomorphic to well, sorry, not t is, but solution to, well, the solution to the equation, t is isomorphic to tau, which depends on t. Okay, so in particular, i.e. what we should have is that rec t dot tau is isomorphic to tau with rec t dot tau plugged in for t. Okay, so to say that rec t dot tau solves that equation is to say that rec t dot tau obeys the property that it is isomorphic to the unfolding of the recursion. So the rules for this new type, recursive type, will essentially codify this isomorphism. So what we'll have, let me do them over here, is we'll say that to introduce this type, how do I create an element of rec t dot tau? What I do is I create an element of tau with rec t dot tau plugged in for t. Okay? What is that? That's one of the maps, in particular the one that goes up like that, of this isomorphism. So we'll call this fold of E when E is up there. The idea being that here we're folding the recursive type, and it's actually easier to kind of pronounce the dual to it. So the other side of it will be unfold, and unfold will have type rec t dot tau for t in tau when E has type rec t dot tau. That's how we'll eliminate a recursive type. So what are the dynamics? Well, the key rule is that if I unfold something that I folded, then I get back what I started. And then, just like with products and sums, you can make fold eager or lazy. If you make fold eager, then you have to step the inside, and it's only a value when the inside is. If you make fold lazy, then you don't have to step the inside, etc. Okay? So what is this equation? Unfold of fold of E steps to E. It's exactly, since we have fold going that way and unfold going that way, saying that if I start here, fold it and unfold it, then I get back to where I started. So it's exactly 1/2 of that type isomorphism, because remember that a type isomorphism is saying that it composes to the identity. The other half should be OK as a contextual equivalence. That is, we should have fold of unfold of E is observationally equal to E. OK. But to develop that kind of thing, you would need some kind of notion of contextual equivalence. So that's what's called an Ada principle, which sort of says you can expand something. OK, so there was a question. Yeah.
Was this the inductive or the co-inductive?
OK, so I mentioned inductive and co-inductive type as sort of a dead branch, OK, which is that like in a total setting, you can axiomatize inductive types and co-inductive types. OK, the rules for that are in PFPL. You have to do a little bit of machinery. Essentially, for the inductive types, what you say is they're constructed by exactly this kind of fold, and they're eliminated by something that gives you structural recursion for natural numbers, structural recursion for lists, structural recursion for trees, sort of all in one go. For co-inductive types, you essentially say you can unfold them, and they're introduced by something that's sort of dual to structural recursion, which is sort of a generation principle for co-inductive types. OK. Now, what I'm doing here is I'm switching gears, and I'm talking about recursive types in a partial language. This will turn out to be a corollary of that. We'll see in a second. Okay? So for recursive types, you don't have recursion over values of this type as sort of a primitive built-in thing. You really let it fall out of these rules. Okay? So we're going to, but we'll get there. OK, but the notation's a little heavy, so let's reconstruct the natural numbers and maybe lists in order to see what's going on here. OK, so how do we make nat as a recursive type? Well, we already said what it is, right? Nat is supposed to be defined to be rec t dot unit plus t, right? Because that's our type equation that nat is supposed to be the solution to, right? It's supposed to be the solution to 1 plus blah. And our way of saying the solution to this equation is that. Given that, how do we define 0 of type nat? What value of this type represents 0? Fold of in left of unit. What value of this type represents successor of E? Well, what we're trying to come up with is something of type rec t dot unit plus t. If I apply the fold constructor, what's the expected type of the inside? I take the very type I'm trying to construct. I plug it in for t in that, which means I need unit plus rec t dot unit plus t. What is that by definition? The natural numbers. When I unfold above the line, unroll the recursive type, what I get is unit plus another natural number. Therefore, I can say in right of E inside there. Okay, so it's essentially fold composed with that function that kind of, right, it's like exactly the representation of natural numbers in this type that we talked about in the beginning of the lecture with the fold. Okay, so you see that you get the like way of turning this into this out of this kind of thing. What does the unfold construct for recursive types give you? Well, it gives you exactly that direction, which goes from n to unit plus n. What is that direction? Well, we wrote it before. Case analysis. Is this number 0, or is it successor of something? Okay? So what we've got on the table now is a notion of natural numbers, where from the fold we can construct 0 and successor. From the unfold, we can do a case analysis on whether something was 0 or was successor. Similarly for lists, if we did the corresponding thing for list, we would get something where you have nil and cons, and you can do a case analysis that says, is something nil, or is it cons? And if so, when it's cons, you get the head and the tail. Okay? Good? All right. So what are we missing? What can we do with a natural number that we haven't said how to do yet in this language with recursive types, right? So like I gave you some rules for recursive types. I gave you some static semantics, some operational semantics. I showed that you got 0 successor case analysis. What else is missing? Recursion. Okay. So we would want to define, right? So for example, to simulate Gödel's T, we want structural recursion on n. Right? We didn't just say how to write a recursive function on natural numbers yet. Not only will we be able to get structural recursion on natural numbers, we'll be able to get any partial recursive function, i.e. the fixed point construct that Bob was talking about a few minutes ago, just from those rules. This might be a little bit weird if you haven't seen it before. It might seem a little bit weird, because nowhere in this language do we have any recursion construct on terms, right? There's no loops, there's no while loop, there's no for loop, there's no recursive functions. But somehow it's there just from having self-referential types. So the idea is that self-referential types will give us self-referential code. Okay? And it's a little bit tricky to code that up, so let's work on that now. So here's the idea. So I'm going to do this in 2 stages. 1, define a type of self-referential programs and get the fix point construct fixx.e from it. And then 2, define that type of self-referential programs from rec t.tau. Okay, so I'm just going to go by way of an intermediate abstraction that I think helps clarify what's going on in the construction. So here's the idea with the intermediate construction. what we want is a type tau self, or is going to be a type. And the idea is that this represents a self-referential computation of a tau. The introduction form is that self x dot e has type self-referential computation of a tau if, assuming x has type self-referential computation of a tau, e has type tau. So to make a self-referential computation of a tau, what you get to assume is a self-referential computation of a tau. Okay? If we have one, then we can unroll it and get an actual tau. So if you have a self-referential computation of a tau, the idea is that you can tie the knot of the recursion and compute an actual tau by unfolding the recursion. So the dynamic semantics for this are that self x dot e is always a value, and that unroll of e steps to unroll of e prime when e steps to e prime. And then the main rule is that if you unroll a self-referential computation, then what do? Well, you're trying to make an e, and above the line, you're trying to make a tau. Above the line, you have a tau, but it requires a self-referential computation. And of course, what you do is you plug in yourself as the recursive call. Okay? So what's going on here, one sec, is you might call this x here this, because just like in an object-oriented language where this stands for the object in question, what we have here is a variable that stands for the thing we're currently defining by recursion. Yeah?
How is it different than phasing fix and zero?
So, okay, what we're doing now, so remember the two stages. So I'm proposing this as a tool to get between fix and those rules. Okay? So we're going to define fix from these, and then we're going to define these from these. Okay, so by the end of the day, I won't have needed this as a primitive ingredient. It's just a handy tool for explaining what's going on. It just helps break the construction into two stages. Okay? So, for example, suppose I want a GCD function of type nat cross nat arrow nat, and I want to define it by general recursion. What does that look like? Well, what I'll do is I'll view it as a self-referential computation of such a function, which means GCD can be defined to be self this of type nat cross nat arrow nat dot like the code for GCD, and then in the middle of here you would call like this, this of type that self, and then somewhere in here you would unroll this and apply it to m minus n and n, or whatever the recursive call is. Okay, so the idea being, I don't want to actually write out the GCD function, but the point is to introduce such a thing, what you do is you bind a variable standing for the recursive calls, which has a self type. In the body of the code, you can unroll the recursion and then make whatever recursive call you want, because it just stands for an arbitrary function that has that type that you can call on whatever arbitrary arguments you want, like doing some subtraction or some division or some Collat's conjecture or whatever. Okay, good. So how do we, and then if you want to actually use it, then down here, you might define GCD prime to be the unrolling of GCD, which actually has type nat cross nat arrow nat. Okay, time for stage 1, which is to get fix from this. So suppose we have type tau self for any tau. What we want is a fix point, fix x dot e, of type tau whenever e is something like that. Okay. What we want this to satisfy is that fix of x dot e unrolls to e with itself plugged in for the variable. Okay, so our goal is to create a program of that type for any type tau, that is to show that any type tau has recursive computations of values in it, and then to show that it simulates this operational step. Okay? So how can we get something of any type tau? We can unroll a tau self. Right? That's what our elimination rule up there says. It says unroll has type tau if he has type tau self. How can we make something of type tau self? Well, we assume something of type tau self, and then in the body, what we need to construct is, in here, something of type tau. What has type tau? E does, provided we plug in something for x. What do we want to, let me call that one y, just so we don't get confused, because e has an x free. What do we want to plug in for x? We want to plug in something that has type tau. What does y have? It has type tau self. Unroll of y. Okay? There's something weird about the fix point, which is, if you think about how functions work, or products work, or sums work, or something like that, computation arises from an intro hitting an elim. I have a function, when I do an application, it computes. I have a pair, when I do a projection, it computes. I have a sum, when I do a case, it computes. Okay? The fix point is sort of an odd thing to throw in, because it computes without two particle and antiparticle meeting each other and reducing. So what we've done with the tau self type is to kind of break apart the fix point into a value part, an intro part introducing the type, and an elim part, unroll. And when the two meet, that is exactly the fix point, right? unrolling a self-referential computation, which, by the way, unrolls all the recursive parts, is exactly our definition of the fixed point. Okay, so what we've done is to kind of break this apart and make it more systematic in a way that follows the pattern for all of the other types. And then you can check that if you define fix in this way, then fix steps to E with this whole thing plugged in for x. Why? Because this unroll of self steps to that with this whole self plugged in for y. So we get unroll of the whole self plugged in for x. And so we're good, right? This step is simulated by the reduction steps there. Okay? So phase one is we can get a recursive computation of any type from self-types. Good on that? Okay. So phase two is how do we get self-types from recursive types? Do that. Remember we had recursive types as solutions of equations. N is isomorphic to unit plus n. List of tau is isomorphic to unit plus tau cross list of tau. Things like that for our data structures. What equation can we solve to get the self-type rules that are on the board there? Sorry, too many people talking at once. What was it? Okay, not exactly that. I mean, it will involve fold and unfold because fold and unfold are the term value and elimination forms for recursive type. But what I'm looking for now is what is the type equation that will guide us towards a recursive type that represents this? Yeah, it's not. I think there's a little bit of a mismatch there. Yeah. Yes. Look at the intro form. Below the line, we have a tau self. Above the line, we have a judgmental version of a tau self arrow tau. Okay? The elim doesn't quite hit the elim. We'll do that in a second. But if you think about the intro at least, that makes sense. So suppose we define tau self to be the recursive type that says t arrow tau. Okay? Then at the very least, we can define self x dot e to be the fold of lambda x dot e. Because what do we need here? If we substitute tau self in for t in this, then that variable having tau self, proving that that has tau, will mean that that whole thing is a tau self arrow tau, which looks like that. Okay? Good? Good exercise in programming by type checking. Unroll of E is supposed to have type tau when E has type tau self. How can we define that? Well, if self is a fold, then clearly we want to unfold. What type does unfold E have? Tau self, arrow, tau. How can we finish things off and get a tau? Well, what we've got now is something that would be a tau if only we had a self-referential computation of a tau to plug in for an argument. Unfold E applied to E itself. Okay. So there's two things to note here, which are maybe familiar to you if you've seen some of like dependent type theory or lambda calculus or something like that before. When we solved these equations for natural numbers, lists, things like that, notice that the variable or the other occurrence of the type that we were defining something to be the solution to occurred inside of some sums and some products with maybe some units around it and stuff like that. When we define tau self, where does tau self occur? To the left of an arrow. Okay? So there's a distinction that is made between what's called positive type operators, where something doesn't occur to the left of an arrow, that's strictly positive, or occurs to the left of an even number of type arrows, that's positive. Okay. There's a more general notion of an arbitrary type operator, which I sort of took on the sly here by saying t.tau, right? In t.tau, t can occur both to the left of an arrow and to the right of an arrow. Okay. When you're solving an equation like this, where t itself occurs to the left of an arrow, that is the extra bit of juice that allows us to define something that is giving us non-terminating computations in this case. Okay? So if all we had allowed was solving equations where something occurs in a positive position, then that's the inductive and co-inductive types that I alluded to earlier in the lecture. If you allow things to occur to the left of an arrow, then suddenly you're off to the races with recursive types in a partial language, right? What we've seen now is that we have types tau self defined as a particular recursive type. Well, we did that. You need to check that, in fact, the operational steps here are simulated by operational steps here. And it's just easy enough to calculate out that that's true. Actually, I think you might need to do something like let x equals e in unfold x applied to x just to get it to come out on the nose there. But essentially, you can make that work. And so then what we've got is self types defined in terms of recursive types. And we saw on a previous board, maybe it's still here, that fix can be defined in terms of self-types, which says that overall, if you expand it all out, what we have is fix, that is recursive computations of an arbitrary type, being defined just in terms of recursion at the type level. Okay. Why is it that we somehow got recursion out of recursion at the type level? Right here, you can see it. What we get is a self application. The key point is that recursion at the type level allows us to construct well-typed instances where something is applied to itself. Okay, it's unfolded or something, but morally it's E applied to E. Why does E applied to E give you non-termination, give you general recursion? So if you've done some untyped lambda calculus, you might be familiar with kind of the simplest example of that, which is, suppose I take the function lambda x dot x applied to x in the untyped lambda calculus, and I apply it to the function lambda x dot x applied to x. That is, I take that function and apply it to itself. What is that step to? Well, we take that, we plug it in for x, and we get lambda x dot x applied to x, lambda x, x applied to x. What does that step to? Well, itself, 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 itself. Okay? So the idea of self-reference allows us to define a general recursive fixed point construct, or to define an infinite loop. And really what's happening is that recursive types allow us to type self-reference, type a self-application, and that's giving us general recursion. So if you are in a language with functions, products, sums, and recursive types, then you can see this as providing a very orthogonal set of operations that gives you a fully Turing-complete programming language in which you have access to good representations of data structures as products and sums. Right? We have the idea of functions. We have the idea of pairing together things, which, as somebody asked in the break here, gives you, for example, the notion of mutual recursion by combining the fact that we get a fixed point at any type with the fact that we have pairs of things. Well, what is even and odd defined mutually recursively? We can think of that as the fixed point of constructing a pair even odd of type nat arrow bool cross nat arrow bool. And then in the body, because we're constructing simultaneously two functions by recursion, right, we have access to both recursive calls in the body of the function. Okay? So we have tuples of things, which give you functions of multiple arguments, functions that return multiple arguments, mutually recursive functions. We have good notions of choices of things, right? Some types give you the idea of options, null pointers, programs that can fail, exceptions, things like that. And then out of recursive types, with some very simple rules here, fold, unfold, right? We're just putting in some type isomorphisms. We're putting in solutions to some type equations. We get a very syntactically simple and orthogonal set of pieces that let us put together most programs. And then we can include for all n exists, extend it with polymorphism like yesterday, and now we've got a whole lot more stuff. Okay? So this is sort of the basic type structure of a lot of functional languages, is functions, products, sums, recursive types, maybe polymorphism. Yeah, there was a question. Yeah.
In terms of initial algebra,
Uh-huh.
that would be the witness from the top to the bottom?
So inductive types are initial algebras. Co-inductive types are final co-algebras, right? So in a total setting, that's easy to make precise. When you have recursive types, it gets more difficult to say what's going on, I think. I mean, I think it's not, depending on various things about your language, things happen. Yeah, so it's not an easy subject. Okay, so where are we? Yeah, okay, so good. So just for a few minutes, what I want to do is to boot up for one of the hands-on problems this afternoon. So one of the things we'll ask you to look at is how a dynamically typed language, in a special case, the untyped Lambda calculus, can be seen as a use of these types. Okay? So what does an untyped language look like? If we're going to write down the statics of it, then if I have rules like lambda x.e has type tau1 arrow tau2, if, assuming x has type tau1, e has type tau2, and e has tau1 arrow tau2, e1 has tau1, therefore e applied to e1 has tau2. Okay, so in a statically typed language, I would have those kinds of things. If I want to make this dynamically typed, the key idea is that a dynamically typed language is really a language with one type. Okay. So we'll take all of our typing rules and replace the types in the rules with the idea that, well, yes, it is a program. Okay. So what is the type checking doing there? It's basically just checking that all the variables are in scope. Okay. For example, right, so we'll have that, and then we'll also have that if I have a pair, what type does it have? The type. Assuming that has the type and that has the type. Okay. Now, what we can do to see this as a use of these type constructors is to represent the dynamic type as some type built up out of these operations. And the key idea is that it's going to be a recursive type that gives you structure that lets you interpret all of these programs. In particular, because in a dynamically typed language, a function can be applied to any value in the language to produce any value in the language, the idea would be a dynamic type, a value of this type, has to include the ability to have functions that take arguments of itself and produce itself. Because you can build pairs out of any two values in the language, it has to include that sort of thing. Okay, so we'll give you a hint for how to set that up, and then let you look at how to compile these dynamically typed programs into this language, taking advantage of the fact that you have recursive types, taking advantage of the fact that you have recursive types where the type can occur to the left of an arrow in a crucial way. Okay, so we'll set that up for the hands-on session. Okay, thanks.